Hello everyone, welcome to my channel. In this lecture we will discuss about the adsorption of carbon dioxide and water vapor using the Aspen adsorption. So we will remove the carbon dioxide and water vapor with the help of activated carbon. Activated carbon is an adsorbent and we will use the Aspen adsorption process. So first of all we will open the Aspen adsorption. You can also open it from your start menu. This is Aspen. So this is the Aspen adsorption, Aspen HYSYS, and this is Aspen adsorption. So first of all we will open the Aspen adsorption. This tab will open. Now after that this is the simulation component list. Click on component list and here click on configure property. So click on configure property. Click on use Aspen property system. Click on this one and click on edit using Aspen property. Click on this one. So it will take some time and after that we will go to the Aspen property. So in that property we will select the components. So the components are carbon dioxide and water vapor. So we will select the component and after that we will select the we will use the basic method. So click on yes. So this window will open. This is the component ID type and component name. So component are carbon dioxide and water vapor. Carbon dioxide and water vapor. Water. So click on next. Then select the base method. So I am selecting the NRTL. So you can use another method. So I am using the NRTL method. Click on next. And here run property analysis. Click on OK. So processing input specification and it will take some time. You will check the status. So this is results are available. Now open this one, Aspen property. This is the Aspen property and this is the Aspen adsorption. Click on OK. Click on OK. Open the Aspen property and click on yes. So go to the Aspen adsorption. So this is Aspen adsorption. Now this is simulation flow sheet library. So click on library and then go to the AdSim. So this is the Aspen adsorption. Here you can choose various methods like the steady state gas adsorption process, controllers, gas dynamic process, ion exchanger, liquid process. This is liquid process is used for the adsorption of heavy metal ions or the adsorption of methylene blue or some other dyes from wastewater. These are the models, etc. So I will click on the gas dynamic. This process is for gas dynamic. So this problem is related to the gas dynamic. So I will select gas dynamic and this is the bed gas speed. Click on gas speed. Drag it to this environment. So this is the gas speed. Select it, drag and drop. This is the gas speed. This is select bed. This is the bed. This is adsorption bed and the product. So this is the gas product. Drag and drop. This is the product. Now we will connect the stream to the adsorber. This is the feed stream and this is the product stream. So we will open the stream type. This one. Click on stream type and here you can check. This is the gas material stream and the liquid ion material stream. So this is the gas material stream. Drag this one and drop it. This you should drop it on the on the arrowhead of this blue one. So drop it and here drag it and connect it this. So this is stream number 1. Now again select gas material stream and drag and drop, and this is the product stream. This is the product stream. This is stream 1 and this is stream 2. Now you can rename it. Click on stream and click on rename stream. So suppose this is feed. Click on OK, and this is the suppose rename the stream. So this is the product stream. Click on OK. Now this is the feed and product. Now click on component list and click on default list. So in the default there are 2 components. We have already selected. So select these 2 components. Select this one. Select the 2 components. Click on OK. So now click on the feed stream. Stream number 1 feed stream. So this window will open. Configure block. The model type. So the model can be reversible or irreversible. So I am using the irreversible pressure setter. Click on specify. So here you can see this is the feed molar flow rate. So I am assuming that the feed is 100 kilomole per second, and the feed consists of the carbon dioxide and water vapor. The mole percent of carbon dioxide in the feed is 40% carbon dioxide, and the remaining is water vapor. So the mole percent of water vapor in the feed is, suppose it is 60. Now the feed temperature is 300 Kelvin suppose, and this is the feed pressure. The feed is entering at 1 bar pressure. So this is a specification, and this is a report. You can click on this one. This is report. These are the results, etc. So close this one and then click on the adsorber B2. So here you can rename the adsorber. Suppose this is B2. So I can rename block and give it name to it adsorber. So this is the adsorber. Now double click on the adsorber, and here this window will open. This is the number of layer within the bed. So how many layer of adsorbent is in the adsorber? So there are 2 layer. There is 1 layer in the adsorber. You can select 2 or 3. It depend on your problem. Bed type, so it can be horizontal or vertical. So in some cases the horizontal adsorber can also be used. For example, in the case of cracking reactions, so you can use the horizontal reactor, or you can use the vertical. So this is a vertical column, and this is the one dimensional column. So, okay, there is no internal heat exchanger. So, and this is the description, adsorbent layer configurations, geometry. So click on this adsorbent layer. So click on this one. Here you will see the configuration block or stream adsorber layer 1. So the general, click on general. Here the discretization method to be used, use UDS1. You can select some other method, but most commonly used is this one. So number of node, it can be 20 or 30 or 25. So you can use, I am using 20 number of nodes. Momentum balances or material balances. So momentum balances, you can use the convection with constant dispersion, convection only, or some estimated dispersion, depend on your problem. Now the momentum balance equation, it can be Argon equation or Kozny-Kármán equation, or the Darcy equation, or the Brock constant pressure, velocity, etc. So I am using the Argon equation. This Argon equation is used for the pressure drop cases. So I am using the Argon equation. You can use some other equation, depend on your problem. This is just a simple problem. Now click on the kinetic model. So the film model can be solid or liquid. So the resistance will be provided by the solid or liquid. So I am assuming a solid. So the lump resistance. Now the kinetic model assumption, it can be lump resistance or micro and macro. So I am using the lump resistance model, and the form of lump resistance model can be linear or quadratic. So I am using the linear model. these are the constant. The mass transfer coefficient is constant or variable, so it can be changes or constant. So I'm using the constant mass transfer coefficient, constant. And then this is the kinetic model, isotherms. So there are various isotherms. Isotherms mean constant temperature curves. So there are various isotherms, like Langmuir, Freundlich isotherm, etc. Temkin isotherm. So these are various adsorption isotherm. I am using the Langmuir one. The one is for constant temperature, and the two is not for constant temperature. So this is the Langmuir isotherm at constant temperature, and the isothermal dependency. So the isotherm will depend on the either concentration or partial pressure. So I am using the concentration. These are mostly used for liquid, but in some cases we can also use for gases concentration, and these partial pressure is mostly used for the gases also. So I am using the concentration, and this is isotherms, and this is the energy balance. So this is isothermal process. So I will assume the isothermal. You can also use non-isothermal process, but I am assuming isothermal. This is the energy balance, and there is no reaction. So there is no reaction, and this is the procedure. This is the click on specify. So here the height of the adsorber. So the height of the adsorber I am assuming 1, and the internal diameter of the adsorber. So it is I am assuming 0.2 meter, and the interparticle voidage I am assuming 0.3 suppose, and the intraparticle voidage I am assuming 0.1, and the density of the catalyst particle or the density of adsorbent, so I am assuming 700 kilogram per cubic meter. Now the adsorbent particle radius, so it is 0.001 meter, and the sphericity of the particle or adsorbent shape vector, so I am assuming 1. Spherical particle, I am assuming spherical particle. Now the mass transfer coefficient, constant mass transfer coefficient for the carbon dioxide is I am assuming 0.04, and for the water vapor I am assuming 0.03, and its unit is 1 divided by second. So you can change the unit 1 divided by second, and this is the 1 divided by hours, but I am assuming 1 divided by second. And this is the isothermal parameter, IP, carbon dioxide, water. So isothermal parameter for condition number 2, for condition 1, etc. So I am closing this one, and here initialize, click on initialize. This is close this one and initialize. So click on yes. This is the results. Click on results. You can also check the results, open, save, etc. Now close this one, and then go to the product stream. Here the model type is the reversible pressure setter, and the enable reporting is true. Okay, click on specify. Here the product molar flow rate. So the product molar flow rate will be same 100 kilomole per second, and I'm changes the carbon dioxide mole fraction. So the carbon dioxide mole fraction in the feed was 40, and I am assuming it 20 in the product, because some carbon dioxide is adsorbed on the adsorbent particle, and the mole percent of the water vapor is I am assuming that it is 30. So this I am assuming 30, and the temperature is constant. This is a isothermal process, and the pressure is changes. I am assuming 3. So click on OK, and click on OK. Now go to this one. This is the run option. Click on run option. Here you will see the communication 1 second, and the displayed 2 or 1. You can change it. Time now it is 0 second. Okay, and pause after. So I will pause my simulation after 800 second. Okay, click on OK, and here click on run option. So click on run. So here you will see it will take some time. So at 800 it will stop. 800 it will stop. So now you can plot the breakthrough curves, etc. for the adsorption column. Thank you very much for your attention. In the coming lecture we will see that how can we plot the breakthrough curves for the adsorber. So thank you very much for your attention. If you are new to the channel, please like and subscribe. Thank you very much.